Welcome. Templates are one of the most powerful features in C++ and one of the most misunderstood. Think of templates like cookie cutters. You define the shape once, then stamp it out for whatever type you need. The compiler does the stamping. In this lesson, you'll learn how to write generic functions and classes, how concepts make templates safer, and when templates are the right tool versus when they're overkill. Let's get started. Here's the simplest possible template. We start with the template keyword, which introduces a type parameter called t. Then we define a function that takes two values of type t and returns their sum. The template keyword tells the compiler, this function works with any type t. When you call add with two integers, the compiler generates an integer version. When you call it with two doubles, the compiler generates a double version. One implementation, many types. And crucially, there is zero runtime overhead. The compiler generates specialized code at compile time, as if you had written separate functions by hand. 4 reasons templates matter. First, one implementation supports many types. You write the algorithm once, and it works with int, double, string, or any custom type that supports the required operations. Second, zero-cost abstraction. Unlike runtime polymorphism, templates don't add virtual dispatch overhead. The generated code is as fast as handwritten, type-specific code. Third, type safety enforced at compile time. If a type doesn't support the operations your template uses, you get a compile error, not a runtime crash. Fourth, the compiler generates specialized code for each type used. This means the optimizer can see everything and produce tight, efficient machine code. Templates aren't just for functions, they work for classes too. This holder class stores a value of type t. The constructor takes a t by value and moves it into the private member. The get function returns a const reference. The key insight? The stored type is chosen by the caller, not by the class author. You can create a holder of int, a holder of string, or a holder of any custom type. Each instantiation is a separate class with its own data layout. The standard library is built on this pattern. Vector, optional, shared pointer. They're all class templates. Let's build something more realistic. Running total is a class template that accumulates values. The add function takes a t value, adds it to the running total, and increments the count. The total function returns the accumulated value. The count function returns how many values were added. This works with int, double, or any type that supports plus equals. Running total of int tracks integer sums. Running total of double tracks decimal sums. The data layout and operations depend on the type parameter, but the behavior, add, accumulate, count, stays the same. That's the essence of generic programming. In most cases, you don't need to specify the template argument explicitly. When you write AutoSum equals add of 2, 3, the compiler looks at the arguments, both are int, and deduces that t is int. When you write AutoWeight equals add of 1.5, 2.25, both are double, so t is double. This is called template argument deduction, and it makes generic code feel natural to use. Callers write add of 2, 3, not add angle bracket int angle bracket of 2, 3. The deduction happens automatically. You only need to specify the type explicitly when the compiler can't deduce it from the arguments. C++20 introduced concepts, named constraints for template parameters. Instead of hoping the caller passes the right type, you declare what operations the type must support. The summable concept requires that two values of type T can be added together. Then the template uses summable as a constraint. Template summable T. If you pass a type that doesn't support addition, the compiler gives a clear error at the call site, not a wall of text from deep inside the implementation. The standard library provides built-in concepts too. std integral constrains T to integer types. Template std integral T means this function only works with integers. Concepts are the modern replacement for older techniques like enable if. They're more readable, produce better error messages, and make your templates self-documenting. Here's why concepts matter in practice. The function increment is constrained to std integral. It only accepts integer types. If you call increment with an integer, it works. If you call increment with a string, the compiler rejects it immediately with a clear message. String does not satisfy the integral concept. Without concepts, the error would say something about operator plus not being defined for string and int, deep inside the function body. With concepts, the error points at the violated contract at the call site. The reader can see instantly, string is not an integral type. That's why it's rejected. Better errors, better documentation, safer templates. Type traits are compile-time queries about types. They live in the type traits header. 4 you'll use most often. Is integral v of t true if t is an integer type? Is same v of t, u true if t and u are the same type? Remove cvref t of t strips const, volatile, and reference qualifiers to get the raw type. Is invocable v of f, args true if you can call f with the given argument types? In this example, we use remove cvref to get the raw type, then if constexpr with is integral to branch at compile time. Type traits give you the building blocks for writing type-aware generic code. If constexpr is compile time branching. It looks like a regular if statement, but the condition is evaluated at compile time, and only the matching branch is compiled for each type. In this print value function, if t is an integral type, we print integral colon followed by the value. Otherwise, we print value colon followed by the value. When you call print value with an int, only the first branch exists in the generated code. When you call it with a string, only the else branch exists. This is powerful for keeping one generic implementation readable when only a small part of the behavior depends on the type. Without if constexpr, you'd need separate template specializations or overloads. Use templates when one algorithm should work for many value types with the same conceptual operation. When the type choice affects data layout or behavior at compile time, and when runtime polymorphism would add unnecessary overhead or complexity. Don't use templates when the behavior truly varies at runtime. That's what virtual functions are for. When error messages become harder to maintain than the abstraction is worth. Or when a normal overload set or interface class would be simpler. The question to ask, does this code do the same thing for different types, or does it do different things? Same thing, different types, template. Different things, polymorphism, or overloads. 3 rules for templates in practice. First, use templates when one algorithm works for many types with the same conceptual operation. Start with the simplest generic function that works. Second, add concepts when callers need a clearer contract. Concepts make templates self-documenting and produce better error messages. Third, stop and simplify if template machinery starts hiding the design instead of clarifying it. Not everything needs to be generic. For next topics, continue with lambdas and move semantics to learn how closures and value transfer work together in modern C++. Then, error handling for exceptions, error codes, and expected. Templates are the foundation of generic programming. Now you know when and how to use them. Thank you.